Piyush, shall we start?
Yes, ma'am.
Good afternoon, all. Welcome to the post-lunch session of day 4 of the Contemporary AI Idea to Product online refresher course, sponsored by AICTE and ISTE, organized by the DYPCOE College of Engineering, Akurdi, Pune. Ladies and gentlemen, let me take the pride to introduce today's speaker, Mr. Piyush Nikam. I'd like to start describing Piyush in his own words. I make machines learn. This is what he says. Because he is a machine learning enthusiast with a strong desire and problem solving skills and loves to engage in challenging work. He is working with Qualcomm Corporation R&D right now, and previously he has worked with NetApp and Manhattan Associates. He has pursued his master's degree from BITS Pilani with a specialization in machine learning. I would like to say with great pride that he is our alumni who has passed out with distinction in the year 2016 and has been among the top 10 students throughout his engineering course. He has acquired various certificates on technical topics such as AWS, computer vision, applied machine learning in Python, on Coursera, TensorFlow, and various other courses on Coursera. So let's welcome him together and let's start the session with Piyush Nikam. Over to you, Piyush.
Thank you, ma'am. Has everybody joined? Could we start? I've presented my screen. Is it visible?
Yes, it is.
Okay. So in today's session, we would be covering a very small application. So we would be building a computer vision model. Okay, that's clear. And I hope you guys must know what computer vision is, but we will go into slight variations of computer vision, that what all it's called, and even we will go that what do we do in computer vision. But first of all, you must have heard people that whenever we are talking about computer vision, they say, let's use CNN. Is it a right way to think about it? Because machine learning, it's not only just taking in models, using those models, getting in some data and outputting some values, and based on that, just prediction. It is something that you will be using in the real world. So just thinking about a task based on a model, it's not right. Thinking about a task, what variations that the task might have, and based on that, thinking, do I require a specific kind of model for this use case? And if I require this specific model, what all parameters or what all things there are inside the model that I can change or maybe fine tune to enhance my model? That is how you need to think about. Because it's very easy to go around on internet and actually Google stuff, get few models, just train your data with train your model with the data that you have, and just corresponding you get the values, and you will definitely get some accuracy, and that would be around 80, and you might be happy. But that 80% accuracy is not good enough in real life scenarios, because in real life scenarios things change dynamically, and you need to be able to change your model based on that. And for that, you need to know your model in depth. If there is a layer, why that layer is present over there? If that layer has few units, how many units are there? Why only those units? Should I increase the units or should I decrease the units? Now if I'm saying units, I'm talking about nodes. So we will be covering what are nodes and what everything is. But this is a hands-on session, so we won't be going into a very depth session because that would be totally a classroom session kind of stuff. But in case if you have any doubt anywhere, you can just ask the question right here, there itself, and we will get in depth for that corresponding topic. Okay, so this is the topic. Do we really need convolution neural nets? Because I've heard so many people that whenever they think about computer vision task, people say use CNN. Why should I use CNN? Everybody started with DNNs. So, okay, first question. When I'm talking about CNN, DNN, everybody is aware of neural networks. I'm assuming that everybody is aware of neural networks, right? You can even type in the chat box that if somebody is not aware of neural networks, I can just give a brief idea on what it is. Because many people only work with machine learning models and not deep learning models. So neural networks you should be familiar with. Now I am assuming that everybody is familiar with neural networks. So let's think about that. Why do we need CNNs? Okay, this is the thing that we will be covering in today's session. Okay, let's continue.
Piyush, sorry to interrupt.
Yes, ma'am.
Uh, Participants, because we have got some participants who are from other branches as well.
Okay.
So if anybody really wants the introduction of neural networks, we can get it done, provided participants want it. So participants, please, those who are from other, mechanical or civil branch, please, you can raise the point and we can continue with a bit of introduction.
Yes, ma'am. Because otherwise, when we start the hand-on session, there will be few syntaxes in TensorFlow, and that time things won't be very clear if you don't know what a layer is, what a node is. So if somebody, we can just cover it for you.
Better.
Okay. Okay.
Thank you.
So for the brief overview, I have one thing in my mind that I will be sharing with you. I'll be sharing a different screen now. So is this screen visible?
Yes, it is.
Okay. So now what are we doing here? Just a second. Yeah. So in this, we will be covering, do we need CNNs? Yeah, but you must be seeing there are few tabs. So this is the data set that we would be using. This is the TensorFlow homepage that we will be covering. So the hands-on session won't cover just coding part. I will be talking about that whenever you are coding or whenever you are even thinking of an application. So TensorFlow and PyTorch are just the tools for you, but how to use those tools effectively. So I will definitely show you that this is the TensorFlow page. How do you go about things? How do you identify what things to use? What are the arguments and do they have a research papers corresponding or not? But just to give an overview, I have this research paper. So this is an introduction to CNN. And if you are working in ML domain or if you're interested in ML domain, even if you are just working on maybe some application, it may be practical application or you're working in an industry, it's a very good practice to actually just briefly get into few research papers, whatever you're using, and just read those. I'm not saying to read all the proofs, but just open the research papers, whichever they must have published. So this is 2015, and just open it and go through the brief idea that what they proposed. Because now what you must be reading CNNs, there are so many variations, people have created so many networks. But what was the fundamental original idea we should be aware of? So this is that paper. Yeah. So now people who don't have a very in-depth idea, we would be covering, these are neural networks. So if you can see this is a very basic neural network. Okay. So this is the input layer. We will be covering input layer, and I will be telling you that whatever you see here, that is the thing that is getting mapped while we are in the hands-on session and while we are using the TensorFlow syntax. So we would have an input layer. Why do we have an input layer? We have some data and we are passing some input here. Now that input may vary based on your application. Just for this session that we are dealing with computer vision models, so your input is an image data. Now image is not passed directly, that we will be covering when we are actually coding it. We will use a flatten layer. I will definitely tell you what a flatten layer is, how do we flatten images, and what happens while or after we flatten images. So don't worry about that. Now we have the input layer. Okay, this is clear. So a neural network is a network where we have different neurons, or you can say nodes. And based on this, We are creating a graph. So if I say a graph or if I say a model, this is the entire graph or an entire model. Okay. So we have an input layer. So once we have an input layer, the inputs are passing from the input layer. Okay. Now we have a hidden layer. In this specific model, there is only one hidden layer. But in case if you want more hidden layers, you can definitely create few different, maybe n layers here, and those n layers would be called as hidden layers for your specific use case. Okay, this is a very simple model. So they have input layer, hidden layer, and output layer. Any doubt till here? Because this is a very basic structure of any maybe DNN model, or maybe you can say MLP model. Okay, so this is what a model means in DNN or maybe MLP, if somebody is saying. If you have any doubts, you can actually raise it in the chat. I would assume that whatever I'm conveying, that you are getting it. Okay, so this is a very simple three-layer feed forward neural network. Now, I'm not saying anything regarding feed forward because that might distract us from the topic. If there is something that we should be covering for this hands-on session, I will definitely go in depth regarding it. Okay, so this is one part. Second part, if we go down in the research paper, why I am covering this research paper? Because it's a very good practice. The original research papers, if you actually go through, they are pretty simple. They're just written in plain English. You can just go through it, and then you will get the original idea that what they were thinking of. Now, in case of CNNs, I'm just covering in brief. I have made a presentation also. I will be covering there too. So this is a kind of an input. Okay. Now this is a digit that we know, but for a computer to understand that this is a digit and this should represent 0, it might be a character 2, it can be O2, but just for this example, let's assume this is a digit. So in a CNN, we have certain specific layers. Those are the convolution layer. The name CNN is given because we are using this convolution layer. If we don't use a convolution layer, then because CNN is convolution neural network, so that name comes because we are using this convolution layer. What does the convolution layer do? Why do we use it? What is the convolution operation? That we will talk about when we are actually doing the hands-on session and in the CNN part of it. Okay. Then we have few pooling layers. That's fine. What does pooling layer do? We will go in depth that time. Then we have fully connected layers. And this is fully connected layer with ReLU. So I hope you guys know what activation is, but even if you don't know, we will cover slight basics of it. So there are different activation functions that we can use. They have mentioned ReLU over here. Why ReLU? We will be talking about not in depth, but we will be just covering that why they have used ReLU. Nowadays, people are preferring ReLU because that speeds up your training process. Now, just using a different activation function, how does it speed up your training process and maybe inference also, that we will see. Okay. Now this is a fully connected layer with ReLU. This is a fully connected layer without ReLU, and then your output layer is connected. Okay. So what we have seen, this is a simple CNN architecture that we will be covering today. And before that, we had seen a simple model. So whenever I say there is an input layer, you should visualize this. Whenever I say there is a hidden layer, you should visualize this. If suppose I say there are multiple hidden layers in your model, that means you can just copy paste this into multiple segments. So those will be multiple hidden layers. And whenever I say output layer, this is the output layer I'm talking about. Output layer is what the model is the entire graph that is telling about your input. Is this clear? Okay. So let's assume that everybody now knows what a neural network is and what a CNN is. Okay. So we can come here. So this is the part where we will start. Now, one thing, this is Colab. So I hope everybody knows what Colab is, but if few people don't know, let's go just an overview. So Colab is, if you can see the URL, it's a Colab research, google.com. So this is a place, maybe a cloud-based application process, a company, It was earlier driven by somebody else, but now Google is owning Colab, or maybe it's just Google is the parent company for them. So what we can do by Colab, they are giving you a service. So they have a Jupyter notebook. I hope everybody is aware of Jupyter notebooks. In Python, if you want an interactive application, so you must have used IDEs for C, C++. Now for Python, they have Jupyter notebook has will also come for other languages. I'm not talking about that. But for Python, what they said, let's have a Jupyter notebook where people can type single lines and then they can execute it. And based on that, everything is GUI friendly. So people who don't know a lot of coding, who cannot write scripts directly, they can actually go about and creating their models too. So this was created for that ease of use. Plus, it's a cloud-based service, so you can add more people. So this we are using. Now, what is an advantage of using Colab? It's absolutely free. There are few limitations, but for just learning purposes, it's good enough. Now, first of all, whenever you are using Colab for anything related to deep learning, I'm not talking about machine learning. Machine learning, I know deep learning is just a subpart of machine learning, but I'm talking about deep learning models. Always go and check your runtime. So runtime is, if you go and change runtime, it's saying hardware accelerator. Hardware accelerators are the accelerators like your graphic card, or maybe you're using a TPU. So if suppose you're using basic ML models, maybe linear regression or something, then you can actually use none. But if you're using, or if you're planning to train any deep learning model, please use GPU or TPU. Based on that, you can actually Google GPU and TPU and get the differences. I hope this part is clear. Okay. Now let's go and check few things. Yeah, I will just yeah, stop my sharing and I will share something the other screen. So I hope this introduction gives you a brief idea that what we are trying to achieve over here, and based on that we can actually proceed. Yeah, and I won't be changing the slides much. It was just once to actually let you guys know that what we are doing. Okay, so this is clear that do we what we are answering. So what we will be covering in this session. That's fine. Now let's go and cover some things else. So other things that I want to cover is, yeah. So this is the agenda for today. So first of all, what we will be doing, we will be going into a small introduction, which I've already covered, but I will just tell you what computer vision is. That is the first thing. Then we will be covering our task objective. What is our objective? So if suppose we have a data set, we have to create a model, but there has to be some objective, right? What model or what kind of model and what the model should do, that we will be covering there. Then we will be going into the basics. This is what I was telling you, that don't worry if you don't know what an MLP model is or what is a flattened layer. I will just go into slight brief details about it. Okay. Then we will be covering CNN basics. Then a comparison that will be the part of the hands-on session itself. So we will do some comparison because we have to compare an a normal MLP model, or you can say DNN model, with a CNN model, and then check, do you really require CNN, or is CNN effective enough or not? And then some evaluation that we have created a model, is it good enough for our use case or not? Okay. Yeah. After that, okay, so let's start with introduction. If you have any doubts, you can just ask in between and we can just go about it. Okay, so this is just an introduction. So what do we do in computer vision? First of all, if we are dealing with computer vision models, we should know that what do we really do in computer vision. So given a two-dimensional data, now if we are saying that we are giving a two-dimensional data to a computer or maybe to a model. Now whenever I say model, think about that representation that we saw in the paper. So given a two-dimensional image, a computer vision system must recognize present objects, all the objects that are present in that specific image and their characteristics. It's very important. Now, there are so many characteristics. A computer vision model should identify those characteristics based on that specific use case. I won't tell the model that identify every characteristic because that might make the model quite slow. So for a specific use case, I want to identify specific characteristics. Okay. Now, characteristics could mean many things. So it could be textures, it could be colors, sizes, spatial arrangement, and many other things. And after identifying, provide a description as complete as possible to the image. So whenever a human is viewing an image, it's very easy for us to tell that what's there in the image. But to make a computer learn what everything is there in the image, it's not very easy. That's why we have to train the models a lot. And after training, we then identify that the what the model has trained on and what it is actually telling us. Is it good enough or not? That's the evaluation phase. But what we do in computer vision model is just this. Is it clear? Okay, let's continue. Now, what is the task objective? Okay, so let's see the objective that we have for today's session. So we have a data set. Okay, that's good. We have a data set. Data set is SVHN. We will see what this means. I have not given the full form, but this is street view house numbers. So in a street view, whatever house numbers are there, people have clicked their photos of the house number, and based on that, they have created a massive data set. Now, this data set consists of images of house numbers. That's why street view house numbers, okay, which is a real world image data set for developing machine learning and object recognition algorithms. Okay, that's fine. With minimal requirement of data processing. Yeah, what are they telling us? That they have already processed the data a lot. So we don't have to actually go and process the data. Why they have done it? So that you focus solely on creating a model. Why I have selected this data set for today's session, so that we focus solely on creating the model, because creating the model was our focus right now. But whenever you are dealing with a real life application or maybe a real world application, you will definitely need to spend a lot of time on data pre-processing. This is the major chunk of your project. So if suppose it's a common saying that whenever you are actually dealing with a machine learning project, 70%, give or take, maybe it could be 60 if the data is really good, if you are lucky, and it might go to 82. So this 70% of the time you are actually working on data pre-processing. Once the data is processed, creating the model and getting inferences out of your model, it's pretty easy. It's not a hard task. Then optimizing the model will take a definitely a different level of task. But majority of your input or maybe majority of your time will go into data pre-processing. Okay. Yeah. So MLP basics. Before going into the hands-on session, I wanted to discuss few things here, because while in the hands-on session, we would be using flattened layer, we would be using dense layer. So at that moment of time, you should know what a flattened layer is, what a dense layer is. So first of all, is everybody aware of this? If you're not aware, you can actually tell me right now, so we can just go into those things and we won't be covering everything else. If you're not, then we can try to cover a few more things as well, because otherwise I can continue without even covering this. So I'm just reading the chat box. If you have any doubts, you can just tell me right now. Okay, so let's assume everybody is knowing what a flattened layer is, a dense layer is, but still, I would just cover it very briefly so that I'm sure that once we start the session, everybody knows what a flattened layer is. Okay. Yeah. So I will be covering what a flattened layer is. So first of all, before even thinking about the flattened layer, we will think of our image first. So if suppose we have an image, is this visible first of all? I hope this is visible. If it's not, you can tell me and we will sort it out.
The red rectangle triangle you say?
Yes, ma'am.
Yes, it is visible.
Okay, and I see in the chat that explain. Okay, fine. Then I
I
will
think that's
even,
about flattened layer, yes.
yeah. Yeah, so we will just go in brief. So what we are dealing with, we are dealing with flattened layer right now. Okay. We should know this intuition because once we are starting to create a model, then we cannot come back here again and then think, because otherwise that flow will go. So what a flattened layer is doing. So if suppose you have an image, for now I'm just using one color, but just for you, think about this as R, G, and B. So any image that we have, a colored image, I'm saying, that has three channels. So if I talk about channels, these are channels, okay? One would be R, that is a red color. One would be green, one would be blue, okay? Now, how can you feed the entire image with three different channels, okay? Now this has some specific dimension. So if suppose I say not X, if I say some dimension 1 and dimension 2, so this is one dimension of our channel. Then we have green, then we have blue. How can we pass this to the model? This is very important because what we saw that we were passing the inputs like this. Okay. So if suppose this is the kind of channels that we are using, how do you actually pass them? This is where flatten layer comes into picture. What does flatten layer do? It will take the entire data and flatten it in one vector. Now this is a row vector, this is a column vector. Okay, so this is a column vector. What are we doing here? It will have all the data like this. Now I will tell you, this is the R channel, this is the G, this is B. So entire data what we are seeing here in the R channel, that would come over here. Now you would ask that, okay, this is a 2 by 2 dimensional matrix. How would you actually put in here? So you can take any method. It could be column wise, or it could be row wise. Okay, sorry. Yeah, it could be column wise, or it could be row wise, and we will just feed it here. Just for an example, if suppose we have a matrix like this, 1, 2, 3, 4, just for an example. So it could be 1, 2, 3, 4 in one representation, or it could be 1, 3, 2, 4. Okay, so we can just have like this, or we can have like this. So this depends upon the implementation, but this is how you need to visualize it. So we will have the R, we will have the G, we will have the B, and this is what the flatten layer is doing. It is taking an image, and this is the flattened part of it. This is how it's flattening it. Okay, this is one thing. Now we have the dense layer. Now why it's known as the dense layer? That is pretty easy. Flatten was the thing that I wanted to convey more. Dense layer is still fine. So I will just rub this portion. I hope you must now know what the flatten layer is doing and why it's helping us. Okay, this is fine. Now a dense layer, if I say a dense layer, these are the nodes. Whenever you are visualizing, these are the nodes. So if suppose you actually read that there was a fully connected layer also. So if suppose this is connected here, why it's known as dense, I will tell you that too. Now these are the connections. So this node, this corresponding node is connected to all the nodes of the next layer. Because of this packing, that every node is connected to every node in the other layer, that is the fully connected. Now in the dense layer, I'm not saying every node of layer 1, L1, and this is L2. Every node of L1 and every node of L2, if it's fully connected, means totally connected, then it's a fully connected layer. If it's not fully connected, but there are a lot of interconnections or lot of connections, even then we say it's a very dense network or dense layer. Okay. Why do we use it? We will see in the hands-on part. Batch normalization, it's very easy to think because it's not just used in deep learning models as well. Have you heard about normalization? Normalization is just taking an input and getting it into your scale. Now, I hope normalization is known to everybody, because if we actually go into depth in each and every topic, then we might deviate from the actually hands-on session. So I hope that you know what normalization is. Just to think about batch normalization, whenever we are passing inputs from one layer to another, so we are passing output of layer 1 to layer 2. So what batch norm is doing, it has actually doing the normalization part on this output so that L2 takes in the batch normed layer output of L1. Is that clear? I know that might sound little tricky if I just say L1. So L1's output, when it's going to L2, if you're using a batch norm over here, so whatever output is coming from here, we will have the batch normalization done on that output, and you can say that output has changed for L2. Okay. So if I just say output, just output bar. So what does that means? That we have the batch norm layer here between, or not layer exactly, we have the processing, batch norm processing over there, and based on that, L2 would actually see the batch norm output. Why do we use a batch norm output? That we will cover in short, but you should know why that we are using batch norm. That I will tell you when we are coding. If we don't use a batch norm, our accuracy might dip. That also I will tell you when we are dealing with CNNs in depth. Okay. Now, do you know what an activation is? Now we actually read about ReLU. So if suppose I'm talking about ReLU, in the paper we saw ReLU. So an activation, okay, for activation, I need to actually tell you what a node is. So for a node, you can actually visualize it like this. A node has these two components. A single node would have this. Okay. First we calculate this part. Okay. Once we calculate the Z part, we calculate the A part. A is the activation part. Now, what activation is doing based on Z, I'm not going into detail because few people might not be aware of this. And if we go into detail, it might take a longer time. But whatever the value of Z is, we will pass it to an activation function. Now, that activation function will tell us, is this node output sufficient enough to be activated? If it's not activated, then this node would be off for that corresponding input. What do I mean by off? Off means that that node won't work for that corresponding input. So others node might be activated or might be on, but that specific node would be off. Let's for an example, if I actually tell you on the top left, if this is a ReLU model, this is a ReLU graph. Okay. Now, what I mean to say by activated, if Z value is greater than 0, this is the 0th point. If Z value is greater than 0, this portion, if it's greater than 0, that means it lies somewhere here. Then it's activated. If Z value is negative, maybe it's in this part, then output a 0 value. This is what ReLU is doing. If it's negative, then output a negative value. If it's positive, then output the corresponding positive value, this portion. Okay. This is a very brief idea of activation. So we only require this for our hands-on session. If you're doing anything, if you're creating a new model, then you can go in depth of what an activation model is doing. Sequential, yeah, I will be talking about sequential in the hands-on session. Optimizer and loss. This is one more thing that we should be covering. So let's cover it. What is an optimizer? Okay. Do you guys know about gradient descent optimization? If not, so gradient descent is just an algorithm to optimize and get to an optimal state. So all your parameters in the machine learning model are optimized. Thinking about optimizers, I'm giving you a very brief intuition. If suppose this is a decision space, okay, and this is our target. I'm talking about a decision space, okay, and if suppose we are starting from here, this point, our goal in creating a model is to reach this point. Why do we want to reach this point? This point is a point where your model loss is minimum. So you want to reach a point where your loss is minimum and your accuracy is highest. Okay. So what are we dealing with? We are dealing with few optimizers. Now, what these optimizers would do, those would optimize so that our path actually goes to the target point, goes to the optimal point very quickly. Because if suppose there can be certain aspects, I would just tell you, yeah, we could reach the target by going here first, then here, then here, then here. Okay, then to this target. Okay, this might be one possibility. One possibility might be that you are going very close to it, then far, then close to it, then far, and then in the end you go. There might be few possibilities that you don't go to the near portion at all. You just hop in the boundary. So what our optimizers are doing, it is actually optimizing the path so that from the starting state we reach the optimal state very quickly. Okay, this is clear. This is in very brief idea, but yeah, you should be aware of this. And what a loss is doing, based on the loss, we know that if the loss is more, our model should be trained more, or we should optimize the model. This is it. So these are the things that you should be aware of before even starting creating a model. Okay, so let's start with the hands-on part now. I hope this is clear now. If you have any doubts, you can just type in the chat box and I will definitely look into it. Okay, now let's focus. I will just present my screen again. Let's focus on the hands-on session. Yeah. Okay, so is this screen visible? Yeah, it's visible. Okay, so now it's saying that the runtime is disabled, so we will just enable it. Yeah, reconnect. Okay, so now we know this point, that what Colab is, and now we can start even creating a model. But before creating a model, are you aware of TensorFlow? So TensorFlow and PyTorch, we have few other options too, but yeah, most widely used are TensorFlow and PyTorch. So now TensorFlow is just a tool. It's just a tool so that you can build your own neural network architectures or model. Okay. Before going to creating a model, we need to actually import the data. So for the import part, I would just use the pre-built model that I have for the import part. And for rest part, I will definitely type along with you. Okay. Yeah. So first we will import everything. So let's import. For import, I will just use the pre-built model that I have. So I will just import all these statements, but I will definitely tell you what we are importing, why we are importing. Don't worry about that. Okay. So these are the things that we are importing. So first of all, before starting, always check your hardware accelerator. It's TPU or GPU. If you use none, then your training time will definitely increase a lot. Okay. So let's start with this. Yeah. So now this is running. So first of all, we are importing TensorFlow. This is the most important part. Rest everything, I think it's used in other models, other machine learning, sklearn models also. So you must be aware of that. But yeah, we would be definitely, I would be talking about TensorFlow in detail. Okay. So now from TensorFlow Keras models, we have sequential. Now, this is where you will know that why I actually went to the presentation part, because if we don't go to the presentation part, then we won't know what a flattened layer is, what a dense layer is. I know I didn't talk about dropout, but I will definitely tell you what dropout is, what batch norm is doing. This is Con2D, that is a convolution 2D network. What max polling, we will definitely talk about max polling as well. Yeah. So now we have imported all the import statements and you know why we are importing them. Okay. So let's continue with it. And now this is what I was talking about. The street view house numbers. This is the data set that we would be dealing with in today's session. Okay. What does the data set contain? Before starting any project, you should always see your data set very carefully. because before the model could actually learn, you should know what the data consists. Okay, now this data set is already pre-processed. So we have the images like this, and these are the numbers. And what our objective is, given a snapshot or maybe just a part of the image, not the entire image, just a part of the image, we need to tell what number it is. So if suppose this is the image, they will just crop this part and say what is the number, and the model should output 7. Okay. So this is the task that we are dealing with. Okay. Yeah. So code part, huh? So I do have the URLs. I will directly copy the URLs over here so that we download it. Now you should get the downloaded version. If suppose you're doing it in your local machine, you can just go to this portion. You can go follow this URL. You can download the train and test part, but we are doing it in Colab. So we will just download it here itself, and you will see it's downloading. It's 174 MB, and yeah, it doesn't take a lot of time because it's downloading on the cloud. So it's just taking 6 seconds to download that 174 MB. So now our data set is downloaded. Okay. Once our data set is downloaded, we should actually have a train and test part of it. Okay. Yeah. So this is the test and train part. Now, the pre-processing part, I will definitely use from my pre-built workspace. But while developing models, I will type with you. If you want to type along, it's good. If you don't want to type now, maybe you can actually go and do the hands-on later on. That time I will be start coding on my own. Okay. So this is what we are doing. From the train part, we are storing it in train. The test part, we are storing it in test. I hope this part is clear to everybody. Let's
Hello.
do that. Yeah,
Can you please tell, suppose I have saved my database in the Google Drive. So
yeah.
if I want to use that drive, so what steps we need to take it?
Do you wanna? I didn't get you. If you wanna use the drive,
Data set saved in Google Drive.
yeah, yeah.
Then what are the steps to be written, or what are the commands to be written over there?
Okay, sure. So as you might know, just a second. Yeah, as you might know, that Colab was developed by Google itself, not Google exactly, but now Google is the parent company for it. So Colab has an extension for your Google Drive. So I would just tell you, yeah, uh, yeah, in the screen, I'm just copying that part now. So you have Google Colab, right? You can just say whatever data that you have on your drive, you can just say import drive. Okay. From this import, your Jupyter notebook will know, okay, you want to import something from your drive. Those may be a data set, those may be some files, anything. Okay. After that, you have to mount it over here. Okay.
Hmm.
So what you will do, you will just run this part. You can easily find it. Here it will go and tell you use the URL in the browser. Okay. So once you click here, it will show you all the user accounts that you have logged in your browser. Okay. And once you give that, you will get an authorization code. Just copy that and paste it here and it's done. And then you can start directly accessing your path.
Okay. Thank you.
Okay. Yeah. But just to make it very simple, I'm just accessing it here directly. Otherwise, if you're doing a project, it's a good practice to have a dedicated folder in your drive and then do it. For my other projects, I do have, but just for simplicity, I'm not having it here. Okay, let's continue. So this part is done. Now what we are doing, we have the train part, we have the test part. Okay. Now let's take out that train and test and store it the usual way we do it. Okay. This is how the usual we do it. So extracting training and testing data. So it's training, yeah, and test data. So now for our data set, we will have the train part here. So it's the X train, X test, and Y train and Y test we will be doing for evaluation. We have done it like this is fine. Now in any deep learning model or maybe machine learning model, you should always and always check the shape of your data. That's the prerequisite, that you should always check shape. If you are if you want to create a model and if you want to debug the model later, if you're creating a very big application, you should always know what the shape of the data is. Okay. Now the current shape of the data is 32 by 32. Now 32 by 32 means when I was drawing an image RGB channel, I was saying D1 and D2. So D1 and D2 is the dimension 1, dimension 2. So dimension 1 is 32 cross 32. So dimension 1 is 32, dimension 2 is 32. So it's a 32 by 32 cross images. Okay. We have three channels. What does this represent? That we have colored images. Okay. And these are the number of images. Is this clear? Okay. Let's continue. Now, why were we even worried about the shape? We were worried about the shape because while processing in our models using TensorFlow, it wants shape in a specific order. It wants the number of images. The n value should be the first dimension and then 32, 32 cross 3. Okay, that's very important. Just to make it compatible with the model APIs, we need to reshape our data. Okay. For reshaping our data, we have a very simple tool in NumPy library that we will be just covering. So change the dimension to samples. Samples is the total number of samples that we have. Side is dimension 1 that we were talking about. I can just say this is the D1 part. This side is the D2 part. And the channel. Channel is telling you how many channels do you have. These are the colored images. So we have 3 channels. So this would change our dimension. Okay, why did we do this? We did this so that our this dimension comes to the first part. So what is it doing? For this data set, just use this to this. Okay, what does this mean? That bring this dimension is -1 in Python is the last one. Bring this dimension to 0th part. So it will automatically bring this dimension to 0th point. Okay, this is clear. Just to make it clear, I will just use one more function, and that I think so. If time permits, rest I will just type it, or rest I will just code along. Oh yeah, okay. So yeah, so this is what we are doing. I'm just randomly displaying 5 images so that we are sure this is the data set that we have. It is just using matplotlib. So we here I'm just using a random index. You don't need to worry about random index. If you are not using a random index, you can give any index, and based on these numbers, you can just say print the image at index 10, 100, 150, something. I'm just using random so that every time I run this, I get different set of images. Okay, so this is a data set. Now see, this is the data set. Now with a human eye, we could actually think, okay, this might be 1, this might be 0, so this is 10. This is how it's labeled. So this is our X part. And what is the corresponding label for it? That's the 10 value. This is 8, so it's written 8. This is, we don't know if it's 81 or if it's 31. So we are just identifying 1. So our model should identify 1. So these are the images. Now you can see how tough it's for the model. Now let's train the model and let's see how efficient our model is, or maybe how can we improve it. There's one more thing that we should do is encode our, okay, I will just first, okay, let's create an MLP model. Yeah, and you can actually do everything here. So this is what a Jupyter notebook would give you over here, that once you have the model, you can just have number of cells here. So you can have the entire project and still be able to read the entire project very properly if you properly arrange everything. So I'm just telling you, this is not part of modeling, but yeah, if you just put 2 hashes, so it will automatically make it a subgroup. So if suppose this is there, and now I say text, and if I say 2 and it says subpoint, okay, so it will automatically make it a subpoint. What a subpoint means, that everything is inside this header. So automatically it's saying 2 cells. And why it would help you? Because if you go to the content, it is organizing your content in that manner. in a hierarchical format. So it is kind of an indexing that you will have tables of content. And later on, if it's a very big project, this will definitely be useful. Not a project for maybe real world application, but maybe if you're researching or just solving a problem or maybe creating an entirely new model, this would definitely help. Okay. So yeah, for now, I will just delete this part because we don't need it. Yeah. One last thing that I will just take from my pre-built workspace is the categorical part, and that's it. Then we will actually go about it and typing it. I hope till this point, everything is clear. Now we are starting to build a neural network. So let's get started. Okay. This is very important that why are we using one hot encoding over here? So first of all, does everybody knows what one hot encoding is? If you're not aware, then I can just give you one brief idea. One hot encoding is used. So now our y values, what we were discussing, if we go here, our y values are labels. So we have a total of 10 classes. Okay. One class is for one digit. So if one is represented by one label, so that's one. So that is one class. So we have 0 to 9. So we have total 10 classes. Okay. Now that y should be encoded in a manner so that our model understands that there is no correlation between that 0 and 9. For a higher number 9, the model shouldn't think that this is more important or less important. For those kinds of scenarios, we use one hot encoding. You can go into depth in one hot encoding. If you don't understand, maybe today, just try to read it. If you don't understand, then we can discuss it in tomorrow's session. Not an issue. Okay. So what are we doing? We are just using one hot encoding on the Y part of it, not on the X. X is our images, only the Y part of it. Okay. I hope this is clear. Now let's create a model. Okay. Now, when I say units, you should be aware of units. Okay. So let's say we have units, we have few units and maybe say L1. So this is our layer 1. Okay. Let's have 5 and 2. Okay. So these are the number of nodes in that layer. In that layer 1, these are the number of nodes. Okay. Let's have 2 layers. Okay. So I'll just copy this, paste it. Yeah, 256. I'm just keeping 256. You can have the number can be decided by you. That's not an issue. You can have different number of units and different layers, and then you can evaluate your model. Based on that evaluation, you can increase or decrease the layers. It's not a hard and fast rule. Just here I'm using these numbers. It's just an arbitrary choice. It's not something specific, and there is no specific order that you should be using 5 and 2 then 256. You can use it what you feel, and you can increase or decrease the numbers based on your scenario. Okay. Yeah. And I'm just using 128 512 256. That is just the way I use it. If you want some other values, you can use it, but if you use these are factors of 2. So these are just powers of 2 to the power something. So that would be very easy to compute. That is just the way computer works. So that is why we are using these. Okay. Is this clear? Now we have units in layer 2 and layer 3. Okay. One more thing, we have an output layer 2. Okay. So we will say units in output. So we saw that we have 10 classes. So let's make 10. After that, I was talking about sequential. Okay. So whenever you encounter something from TensorFlow, which you are not aware of, so always go to the TensorFlow homepage. Whenever you reach here, just select the API and just go to the current version that is running, that is 2.4. If suppose you want a specific version, they have a feature for that too, that you can request for a specific version. So now you are at Python this. So you have different APIs also that you can view. After this, we can just come to Keras sequential. Why I'm showing you this? So that you are aware that whenever you are building your own project, where should you look for and what should you look for? Okay. So this is TensorFlow. Keras sequential. This is what we are using. So sequential, what is it is doing? It's just stacking layers. Okay, it's just a method, or it's just a way of stacking different layers. So we will be creating a different layers. We will be stacking it, and that entire stack, we are calling it as a model. Okay, and this side, right side portion of it, you will have all the methods that you can use on your sequential model. Okay, so if you go on the methods, if you want to add something, you will have add, and you can just give layer, and you have all the arguments. So this is how you use it. But for now, let's go here and create a model. So let's say we say it's a model, and we say it's sequential. Okay. Yeah. Now sequential, you can just give here. If you already know the layers, so there are different ways of doing it. We know that we will be having few layers and an output layer, so we can just directly write all the layers as a list, and we can just pass it to our sequential class, and that class will mm, pack everything into layers and give it to our model. So this is how we are creating a model. There is another way of creating a model that we won't be discussing it today, but definitely tomorrow we would be discussing a different way of creating a model. Okay. So now here comes the flatten layer. Now you know what a flatten layer is. So what are we doing? Now it has, we have to give the input shape. That is very important, so that it knows how to actually flatten your input shape. And we have the xtrain part, right? So xtrain is there, and xtrain's 0 dot shape. So we are just giving the shape first. So it knows that this is the kind of shape it would get when we start training it. Okay, this is fine. Now we have the dense layer. So we go in the dense layer. Now we have to supply units. So why I was saying units? Because we have to give units, because in the parameter they have named it as units. So that is the why I was saying units. But you can, just for thinking, number of neurons you can say, or number of nodes you can say, but here it's known as units. So units, we have already given units in layer 1. Okay, so will it show? It's not showing because I've not compiled it. Okay, layer 1. So that is our units for the first dense layer. And let's use an activation function, and let's say we want to use rel. Okay, now I've given a brief idea what an activation function is doing and what a relu function is. That is why it's very important, before even starting to code, going through what an activation function is, what are different kind of activation functions. So let's go again, and let's come here, and we will see a lot of functions over here. So you can actually go here and check each and every bit, and based on that you can see, okay, these all things are there. And if suppose you don't want to use this, you can just come here and say activation, and it should give you, yeah, so it is giving me a hit in the first place. So we are coming at layers, we are coming at activation. Now activation, you have different activations. So here we are using relu, but if you want to use some other activation functions, you can definitely use it. So it will actually give you the entire usage part. Okay, so this layer activation is fine. So let's copy this layer and just paste it here, and let's change the units to L2. Yeah, this is fine. Activation we want to keep same, and let's have a batch normalization. The only part that I'm thinking, that it's a 2-hour session, and training a neural network model takes time, so we will keep the epoch count less for the session. But when you are training it, you should actually have an epoch count maybe slightly higher, so only then you will get the desired accuracy. But for now, let's keep a very small training session. And if suppose time permits, I will definitely show you, if we remove batch normalization, what's the hit on accuracy, if time permits. Otherwise, you can actually do it on your own. It's very simple, just remove that layer. So we have the third layer, and let's have the dense layer in the end. Yeah, and we will say this, let's give the output Let's not make the model very big. Otherwise, the problem would be that in this time span, this 2 hours time span, the model won't be trained because it might take a longer time. For last, it's a thumb rule that you should use softmax. If you don't know softmax, if you're not aware what a softmax activation is, today what you can go, you can read about softmax. If you still have a doubt, we can definitely discuss softmax in tomorrow's session. Okay. So this is softmax. This is the entire model. So now you must be saying, okay, we have used 2 dense layers. Yeah. And the last one is the output layer. That's fine. And the flattened layer. Okay. We have created a very small model so that the training time is also quite small. Okay. Let's do it. So now this is, so there's no errors. If there were few errors, maybe some typos, then it would have given it right here. Otherwise, it would give us while training. So let's check the model summary. So now it has outputted in the model and we can just use the summary part. It will display a very nice pictorial representation. Yeah. So what is the model? It is created using the sequential API. Okay. First is the flattened layer. Okay. Second is dense, then dense. So this numbering scheme is just if you use the same kind of layer, it will just number the layer from that place. Okay. The most important part here is total params. Okay. Now see the number of parameters over here and see the number of trainable parameters. I hope you are aware of what are trainable parameters and what are non-trainable parameters. I'm just assuming, but if you don't know, you can actually tell me right now. If I'm just assuming that you know. So if we say there are trainable parameters and there are so many trainable parameters, just think of how many parameters just for a very small model we need to train. And based on the data, we have to train all these parameters. And even if you're storing the model, you have to store all these parameter values because in the end you're training these parameters, and while you're storing the model, what do you store? You don't store the entire architecture. You just store all the values that were trained. So maybe some numeric value, maybe fp32 if you're using, or fp if I'm saying that is floating point. So fp16 value you are storing, or maybe fp32 value you are storing. So you're just storing that, but storing it for such a large number of parameters will definitely make your model too big to store. Not too big, but definitely bigger than other approaches. Okay, this part is clear. Let's now start compiling the model. So there is one part. Okay, so I will tell TensorFlow, okay, to compile my model. Yeah, compile. Yeah. In compiling, we have few options. That is why we were talking about those options earlier. So I have an optimizer. Okay. Now I have an option of giving any optimizer. For now, I will be giving Adam. Again, the only point I'm again considering or assuming that you know all this stuff is because deep learning, there are so many prerequisites before you even start a hands-on session for deep learning models. So I'm just assuming that you are knowing this thing. But if suppose you don't know what an Adam optimizer is, I will just briefly show for Adam optimizer. Now, based on that, you can actually, if you don't know any of this bit, you can go to TensorFlow and you can directly search for it. Just assuming that you don't know Adam optimizer, what you can do is you can go to TensorFlow. If you are not very keen on going to optimizers and then finding Adam, you can just type Adam optimizer here. Okay. Otherwise, in optimizers, you will have all sorts of optimizers. So there are so many options. We are using Adam. Okay. This is one point. The other point is, I will show you one more thing. Yeah. Why I'm showing you all this? Because just writing a code is very easy. But understanding what the code is doing, what kind of manipulations you could do, that is very important. So whenever you come here, you can just go. There might be few paper links available on the TensorFlow page itself, you can just go to that paper link. So it will directly open the paper which was published for Adam. Okay. I know it's not feasible to read all the research papers, but whenever you're not sure that what you are trying to use, you can just go and briefly read what they were trying to do. Just this part, abstract. And then if you like the abstract, just go and see maybe the introduction part. That if they are proposing Adam, what are they doing? So they have proposed Adam. So what they are doing, they are taking the advantages of two different models. So what they are saying, combining the advantages of two recently popular methods, this one and this one. Okay. So they are combining both the advantages. There might be a few disadvantages that will be in the paper, but while checking the optimizer, so if you have a doubt, should I use RMS prop? Should I use AdaGrad? If you don't read from somewhere that what Adam is doing, you might select that. But Adam will give you the advantage of this and this at the same time. So that is why it's very important to just go through the papers, not read it completely, just go through the abstract and intro. So from here we know, okay, Adam is good enough. Let's take Adam. Okay. And the use case, you already know that how we are using it. Just use Adam like this. So the name is given. So I've just used name like this. Otherwise, there's a different approach of using Adam. You can use it like this, or you can use it like as a function. So it will automatically call Adam optimizer. Okay. I hope this is clear. Yeah. There's a learning rate also. I hope that you might know what a learning rate is, but if you don't know, you can stop me anytime and then I will explain you what the learning rate is. And based on the change of learning rate, how our model behaves. Okay. Yeah. So we have used Adam optimizer. Now for compiling, let's use a loss function. Now I told you that a loss function is used to evaluate so that our model also knows that what it is trying to optimize. So that's why it needs a loss function based on which it knows that am I going to a right point, and will I, based on this path that I'm taking, will I hit the target or not? So that is why we use a loss function. So let's use a categorical. Now, one more thing. I will go again. And if you go come here, you see losses. There are a lot of loss functions available. You can go through it. We will be using categorical. Okay. Why are we using categorical? We are using categorical because our data set has 10 classes. It's not a binary classification. It's not a binary prediction that it's 0 or it's 1. It's a categories. There are different classes. That's why we are using categorical. Okay. Cross entropy. So you can just use the name from there itself. So what you can do is you can just go, come here. Yeah, you can just use this name in your project. I'm telling you, because once you start doing it, you will remember it. But if you're just starting, you might not know there are a lot of options. So just refer the TensorFlow page again and again and just copy and paste the values from there. Okay. And there's one more thing. There is some matrix in a model. Okay. So if there are matrix in the model, which matrix should I focus on? Now you would ask me what are matrix. Let's go and see what are different matrix. I know it's a lot to actually see in one session, but you will definitely get used to it once you start coding, or maybe once you start your hands-on session. And once you have created few models, you will definitely get a hang of using the TensorFlow page and coding simultaneously. So if we say matrix, you can see AUC, you can see accuracy. There are multiple things. For now, just for training our model and seeing the accuracy, let's focus only on accuracy. Okay. So for that, I would say, yeah, I know. Yeah, just a second. Yeah. Matrix assumes that we are giving a list because we can pass multiple. I can say I want accuracy as well as I want AUC score as well as I want something else. But for now, let's keep accuracy. Okay. This is how I want to compile my model. If there is any error, it would tell me. Okay. Now, if I'm telling, I've already told that I will be compiling my model using this optimizer, using this loss function, and I'm only worried about accuracy. So whenever I ask, give me accuracy, I don't want anything else. There is one more thing that we would do is creating a val stop early point. Okay, so I will just type that. Yeah, okay. And while training, usually what happens, yeah, while training, usually what happens that deep learning models take a lot of time to train. So it's not feasible to train the entire model at one shot. So it might take 5 hours for the model to train. But if suppose it's taking 15-20 hours, so you cannot give the entire 15-20 hours at one section. Okay. There might be an electricity cut, there might be an internet issue, there can be something. So it's always advised to create checkpoints. So whenever a model passes some iterations or maybe every iteration, it will checkpoint all the data. It will dump all the data which has already computed, so that even if there is some error in between, you know at till this point the model was at this stage, and from there you can restart your training process. Otherwise, retraining the model again and again for 15-20 hours, it's not feasible. Okay, just for that I will just say file path. But before that, what I will say, val loss. So validation loss is one thing. So it's a training loss, and the other one is the validation loss. Okay, so we are worried about the validation loss and early stopping. I hope that you know what early stopping is. If you don't know, then you can tell me and we will cover that. So what I'm trying to do here, that I would be using early stopping in case that whenever my model accuracy is not improving, or maybe my validation loss is not changing or maybe not decreasing the way I want, it should stop training because the model must have reached somewhere close to the target point. Okay. So I would say the monitor. Monitor is the point where you are actually fixing the value. Fixing the value as in what value you need to monitor and do the early stopping based on which parameter. So that parameter we give it in the monitor. So I am saying val loss. Okay, this is fine. And there is a patience field. Patience is that how many times you are fine with it not changing. So I will just give here 3. So if it doesn't change 3 times, it's fine. It will continue training, or maybe it will continue processing. But even after the third try, if it doesn't change, just stop it, early stopping. Okay. So this is the patience parameter. That is fine. Now let's have the file path. File path, why I'm doing it? Let's have the file path. So we have checkpoints. Why do we need to have checkpoints? We need to have checkpoints because in between, if our model stops, we should always start from that specific checkpoint. It's not feasible to train large models again and again from start. Okay, that's why it's just a file path. So whenever I wanna again bring back the model, I will just use this file path. Okay. Now there was a question that if you are using drive, so if you're using drive, you can have your entire path here, path slash this. So this will be your folder structure. So maybe it would be folder 1 slash folder 2 and so on. So that would be your entire structure. And then you can have the entire checkpointed model. How will that help? You can download this checkpointed model and train it on your local, or maybe give it to somebody else, or maybe next time you want to start it, you can just directly start from this point. Okay, this is fine. Yeah. Now let's create a model checkpoint. It's not always that we need to create model checkpoint, but it's a very good practice to do it so that we save time later on. So there is already a class that is model checkpoint. So we will just use that. I will just say, where do I want to save my model? That is in the file path. Yeah. Don't get confused regarding this parameter and this parameter. This is the parameter that we want to pass for the class, and this is the variable that we have created. Okay. I've just used it the same name so that we don't get confused at what to pass. But yeah, don't get confused. That is just the parameter that we are passing to the class. Okay. And it will say, okay, what's the monitor? Yeah, what's the monitor? I will just say monitor val loss. Okay, this is fine. I've already told you. Now, whenever you're creating checkpointing, the checkpointing of the model could be anything. So at every iteration, it's possible. But just to save space, I will say only save only the best. I don't want anything else. Will it give me an option? Okay, let's see. Yeah. Okay. And we will say true. So what it will do while checkpointing, it will save only the best model. Okay. Because we are only interested in the best model. Now, while saving, I want only weights. Okay. So what I'm doing here, while checkpointing, always put my model in this part. Always consider the validation loss for any checkpointing. Only save the best model and only save the weights. This is clear. Okay, let's come to, yeah, this is fine. Now we wanna fit our model. Okay, let's fit our model. So there is something called as history. Now, if you're not aware of history, by this time, you would know that what I would convey, just go to TensorFlow, check history. So any model class that we are dealing with, whenever we call the fit function, it automatically trains the model. While training, whatever happens, the history part of it, it actually saves it in an object known as history. We are just outputting that history into this history. And based on this history, we can actually check at which point of time, what was the loss, what was the accuracy and everything. Okay. So we will say model dot fit. Yeah, fit. And let's tell that our x part of it is the x train that you guys know. That's the x train. Y part of it was, so y train, but the important part was it was an encoded y train, not the original y train. Why we use the encoded, we have already discussed. But if you still have doubts, you can stop me anytime and ask me. Batch size, I hope you're aware of batch size, but I would still again tell you what the batch size is. Batch size is just that in the entire set, for one iteration, what batch, the number of batch at one shot, what you're giving. So that batch size, I'm just giving 5 and 2. Okay, so yeah, so if you see it says model.fit, you see all the parameters that we can pass. So what we have passed the x, we have passed the y, batch size we have passed, and then epochs, verbose, and verbose and callbacks. There are multiple things we can pass whatever we want to pass. So till batch size, it's fine. Let's see the epochs. Yeah, okay, epochs. Okay, so epochs we will say 10. I would advise you to go for higher epochs. Just for the time constraint, I am doing it for 10. That's it. So that it doesn't train for a very long time. Otherwise, we need to wait. And the entire 2 hours would be spent in this. Otherwise, yeah, a validation split, you can just direct copy paste rather than writing. So validation split, I'm just using 80-20 split. You can use 70-30 as well. So validation split is 0.2 means 20% of the data, store it for my validation. Rest everything goes to the training part. Okay. And then do I have callbacks? Yeah, I do have callbacks. So there would be a callback variable here somewhere. If it's not there, just a second. Okay. Oh yeah. So if it's not there, you can just go on the TensorFlow page and then read it. So callbacks are some callbacks. So if suppose something happens, I want it to connect to my callback function, which we have created maybe previously. So we do have callbacks. Those are callbacks here. That early stopping, that anytime something happens, anytime validation loss doesn't decrease after 3 iteration, call back to my this function, something like this. So I do have callbacks and I will give the callbacks here. So one is validation. It should give me, yeah. and the other one, it's a list, so I can just pass multiple. Other is the model checkpointing. At please checkpoint my model. Okay. So I hope this is clear. So let's start training it. Okay. And let's hope our model trains very quickly. Yeah.
Sir, I
Was
have
there a
question.
question? Yeah. Yeah.
Sir, this validation split regarding
Yeah.
I want to ask, sir, we can give the training. We can divide the data set into training, validation, and testing, right? Can you
Yeah.
tell me how to divide it into three? Means if I am using image generator, so
Yeah.
how to divide into three parts: training,
Okay.
validation, and testing.
Okay, so what we are doing here, we are actually dividing into three itself. So one is only training our model with the test, training our model with the train part. And in the training part also, we have given 80 part for the training and 20% for the validation. Okay. And
Okay.
the test part, we won't be covering the test part right now, only for
But here you
evaluation.
have not mentioned, sir, na, ki how much data set you have divided for training and testing. Where now, right now, you are showing this na train
Yeah,
and test. Here
yeah.
you have not splitted your data.
Okay, so because our data set is comprising of test and train data separately, what you are telling me that you have one entire
Yeah,
chunk and
yeah,
you
yeah.
want to divide it into
Huh.
three parts.
Yes, that I want. Ki how to divide it into three parts: training and training, validation, and testing.
Okay, so there are multiple ways of doing it. If suppose you want a very generic way or you want the full control of it,
Yeah, yeah.
yeah, yeah. So
Can you give me the one example for that
see,
one line?
yeah, one line we can actually search TensorFlow that they might have a generator or maybe something that chunks it off, but it's a very simple way. So if suppose you have xtrain, right? So
Yeah.
xtrain has so many examples. So you can decide that what percentage of examples you want, and you can just pass it xtrain, and you can just keep from 0 to some maybe x part. You can just keep for your train part. I'm just giving you a very brief example if you want to do it very quickly. And then for validation, you can just say my x train validation part could be from x portion. I'm talking about indexes till y portion, and my test part could be x train from y part till the end. So this is how you can easily split it. Don't even need a function for it. But if you need a function, you can definitely go to TensorFlow and you can check it.
Sir, actually, I went through that.
Yeah,
My question is, for example, suppose we are using that ImageNet data set, right?
yeah,
So there are thousands of classes. So for
yeah,
example,
yeah,
I have a data set, I have 100 classes. So
yeah.
that time I am not seeing that how many images I have. In one class might be I have 250 images. In another class I might be I have 400 images, right? So
True,
there
true.
I want to give the percentage that 80% for training, 10% for validation, and 10% for
Okay, I
testing from
got it.
each
So
class. So that
different
there I
classes.
am
Yeah.
using image generator function. But how
Yeah.
to divide into three parts? I am not getting that. I can divide into training and validation, but not
Hmm.
into training, validation, and testing.
So okay, because even I have not used it in that manner what you are saying, but if you wanted, if you can divide it into two different parts, now the bigger chunk you can again divide it in the same manner into two different parts. So that would make it
I
three.
I
But
have
if you
tried actually.
yeah, we can actually discuss this, or maybe I can actually check if TensorFlow supports some specific functionality for use case, and we can discuss it tomorrow. Not an issue.
Okay,
But
sir.
what
Please, you can if you find some.
yeah, yeah,
So
yeah, definitely. Because your case is very specific because your classes are
yeah.
not very balanced. You have, for a certain class, you have a lot of examples, and for a certain class, you have very less examples.
Yes.
Yeah, for that very specific use case, what I think that you might need to write a logic, but I will definitely search if there is a pre-built function for that or not.
Okay. Okay, sir. Thank you, sir.
Yeah. Okay, so we were training our model. So now our model training, okay, this was the first epoch here. So the training part is most probably complete. So let's go and check. Now, yeah, just a second. I'll just print it. Code, yeah. Now we have saved everything in the history part. Okay. Now, based on this history, we can actually plot the entire data for our validation loss as well as validation accuracy to check was our model trained properly or not. Just due to the time constraint, I will just use from my pre-built workspace because we want to build the CNN model also, and yeah, we are slightly short of time. Okay, so what we are doing, we are using matplotlib. From the history object, we are saying all the history of the our model, we want the loss. Okay, so this is the loss, then we want the validation loss. So based on this, we are just plotting it for this. We are not plotting for accuracy. I will tell you the accuracy part as well. Okay, so now you are seeing it's not very good. So orange depicts the validation loss, blue depicts the loss. Okay, so loss, our normal loss is decreasing, but validation loss is not very good. That might be a case because we have used very less number of epochs. Once you start training the model for a longer duration, this might get smoothened up. Okay, but for now we don't have a lot of time. That's why we use only 10 epochs. But in your usual use case, you can use maybe epochs for 200, 250, depending on your training data size. Okay. Now let's go and print our valid accuracy aspect also. Okay. So we are just printing accuracy. So this is the blue line depicts our accuracy and orange line depicts our validation accuracy. Okay. So this is validation accuracy is also not very smooth. That is because of the training that we have not trained a model for a longer period. But still, what we should observe that is the accuracy increasing as time goes on. So in a general sense, yeah, it's still increasing. In a general sense, it's still increasing. Okay, my model is still doing a good job, not the best job, but a good job. But if suppose my accuracy is decreasing, then I need to get worried, or then I need to figure out that what is the problem, and then I need to fix the problem and retrain my model again. So this is how you can actually, just by looking at the graphs, you can get to know that, okay, it's going in the right direction or not. Because if it's going in the right direction, it might reach the target. But if initially it's not going in the right direction, then it won't reach the target. You need to fix your model beforehand. So the loss trajectory should go down, somewhat down, and the accuracy trajectory should go up. Okay. Now the only thing to remember over here is we have got, yeah, I will just use one more thing that we will be evaluating it. That will be the X test, which we have not touched. That means our model wasn't trained on this part. So we will evaluate our model on that, and we will check that what kind of accuracy we are getting. Okay, so it's giving us 56% accuracy. And I would say 56 is not a very good number because the epochs are less. That's why we are getting a 56% accuracy. So it's not a good accuracy. If you train for more epochs, you will definitely see an accuracy increase. Okay. So loss was this and accuracy was this. Now the point to consider here is there are so many number of parameters. So training so many number of parameters and then after 10 epochs getting an accuracy of this. If our CNN model with less number of parameters with same amount or same epochs of training gets more accuracy, then we would slightly be convinced that let's use CNN models for our image task because it's taking less number of parameters. We need to train less parameters and we are gaining accuracy and we are decreasing the loss. Okay, this is the point I wanted to make. So now let's go in that. Now it's 340. Okay, so let's create a CNN model. So I will just say CNN. Yeah. So for creating a CNN model, it's the same way what we have used. So we will be using sequential. Yeah. And we will have certain number of layers. Let's use convolution layer first. Okay. Okay. So now you can see what are the parameters, filters, kernel size, strides. I hope you guys know this. If you don't know, you can actually search it. Otherwise, you can just let me know that you don't know what a kernel is or you don't know what a padding is, then we can discuss that too. So that is the reason that before even building the model, you should be aware of what a convolution neural net is, what a convolution operator is, and what we are doing, what is a padding, what are strides. So I will just, if suppose if this is visible, I will just go back to that again. So yeah, this is our CNN model, a very simple CNN model. So this will be our input. We will have the convolution layer. That is what we are making right now. And then we will have some pooling that I will tell you that we will be using pooling. And then in the end, we will have the output and the fully connected layer. Okay. So always visualize this. This is a very simple diagram which they had proposed, but now your model might differ based on your use case or the way you develop your model. Okay. So let's say 32, and I will say kernel size, not kernel constraint, just a second. Kernel size that is equal to 3 cross 3. Okay, so we will be having a 3 cross 3 kernel. Padding, let's say, let's make it valid. Okay, and activation, you already know that we had already discussed. Activation, let's keep activation as a value only. And we need to give the input because this is the first convolution layer. I need to give at least the input shape so that it knows what the input shape is. So train, yeah, 0, and I will just say shape. So what I'm doing here is I'm just telling the convolution layer that this would be the input shape that you would be getting. Okay, once this is fixed, I can just copy this so that I can use it for my second conv layer. Now you must be wondering that why have I used 2 convolution layer, because this architecture is also valid. So this is why you can just go through and check few things. So what they have mentioned in the paper also, there were few details that you can go through, but I would go in only, yeah. So this is one portion, what they have told us that yeah, a common way of CNN architecture, it's fine, but there is one more way where people use 2 convolution with ReLU. So when we give input and we use 2 convolution layers together, because that architecture is also considered as that, and it's good enough because they have used it in their paper and they said you would get good results. So this is what we are doing. Okay, I will just quickly create the net so that the model training starts. And once training starts, then we can actually talk about the model more, because training would take some time. So we will have time to discuss it. Okay. Yeah, pooling size, I will just give 3 cross 3. Yeah. And let's have a batch norm. I don't think so we would have time for removing batch norm and then training, but yeah, you can just try taking in the batch norm and removing the batch norm and then training it again. You will definitely find a difference over there. Now let's flatten our output from batch norm and let's have a dense layer. Okay, so in the dense layer, I want to have units equals to 64, and I want to have activation layer as activation function as ReLU. Sorry, ReLU. Okay, now let's introduce a dropout as well, so that you know that there is something called as dropout. Dropout is really good. It actually makes our neural network quite robust to changes in the input. So let's have a dense layer and let's have, now I'm not saying that this architecture is the best architecture or this is how you should develop it. Just try different architectures. I've just taken some random very small architecture. So that now let's consider this as the output layer. So I should have the activation as softmax. Why do we need softmax? You can just read about it. If you still have any doubt, we can definitely discuss this tomorrow, that why do we have softmax over here? Why not ReLU? Why does what does softmax gives us that output? It's a thumb rule to have softmax in the output layer. Okay, so I'm just checking if the CNN is correct. So we have 2 conv layer, then we have a max pooling layer, then batch norm is there, then flatten, dense. Okay, yeah, it seems correct. Yeah, and let's print the summary. The thing that I wanted to show you should be seen here itself, so we don't have to wait till the training part of it. Okay, now this is a model Okay, CNN model, sequential one, because we have already taken the sequential in the first place. So it's just a naming convention that it automatically follows. Now we have two conflare, that's fine, max pooling, everything is fine. Look at the number of parameters. Now this is very important. If you see, the total number of parameters are just only this much, 1,76,000. Yeah, that's it. This is very, very, very important. Now see the total number of parameters over here. This is very large. This is around 17 lakhs. So from 17 lakhs, we have come down to just 1 lakh. This means this would increase your model performance because you have to train less number of models, not model performance, maybe training performance, because you have to train less number of parameters. And even for storing, you will have to store only this trainable parameters. Or maybe if you store all the, yeah, we will be storing all the parameters. So you're storing less number of params. That means the stored model size would also get reduced. This is one of the things that I wanted to show. And now let's compile the model. I would use the same compile feature, what the way we have compiled it, because if we change it, then we cannot compare the models. We might think that because we have used something else, that is the reason that it's giving us better accuracy. Okay. Yeah. And let's have, I'm just checking that. Yeah. Let's have this part itself. Why are we keeping everything same? We are keeping everything same so that, yeah, we will keep everything same so that we can compare our models properly. So let's have a checkpoint, CNN. Checkpointing should be there. Otherwise, we might miss few things. Val loss, save best. Yeah, this looks good. We have done this. We have checked the file path. Yeah. Compile is done. This is done. Yeah. Okay. So, that's fine. And let's do everything in a similar manner so that we are sure that whatever we are doing, we are able to compare it very appropriately. Okay, model.fit. Now this model, I can just say it's my CNN model and not my MLV model. Fit. These all are fine. 5 and 2 is fine. Epoch is 10 is verbose, split. Everything should be same. Okay. Let's start training this model and let's what it said. You must compile the model. Okay, I didn't run compile. Oh, sorry. Yeah, I didn't compile my CNN model. That's why the error was there. So now let's compile. I have not used model anywhere. Yeah. Okay, and let's start the training process. Okay, so it's one epoch. Yeah. So now it will take some time to train. So now we have slight bit of time. So let's discuss few things here. Now the biggest point is drastic increase in the total number of params. Now with the drastic increase, if we are able to get equal accuracy or maybe better accuracy, then we know why CNN is important or why we are using CNN for this use case. Will CNN work for other use cases? We don't know. That is why people are not suggesting CNN for other use cases. CNNs are made for specific use cases because they give you certain properties which your dense model won't give you. Okay. What are those properties? We could actually discuss if we are looking at this figure. I will just tell you here. It's better to tell it from here so that you can even map it. If I just tell you looking at the code, then you won't be able to map it. So this is the convolution layer. Okay. What is the convolution layer we are doing? So if suppose this is the image, fine. Now in this image, we are looking at this portion. So we can have 4 portions. Based on this, we are taking the entire chunk. If you see this square, entire chunk, and then we are checking, is there something relevant in that chunk? And then we are shifting this part to this stride by 1. So that's just the stride. So we will shift it by 1. And then we will continuously shift it till the entire image is covered. And just by shifting that portion, what we were looking, we will just always ask, is there something relevant in that part? If there is something relevant, we will only check that relevant part and store that relevant part. We don't need to worry about each and individual bits or each and individual pixels. Okay. So that is why, just because of this, that we are taking one region and checking if there is something important rather than looking at one pixel by pixel. That is the reason our number of trainable parameters are less. Because if we check pixel by pixel, then the training parameters would definitely increase. To reduce that, we are just checking region by region. If this region is good, okay, I will just say this region is important. I won't say which pixel in that region. That can be later on step. Okay. I've just given you a brief idea. If we go into detail, we can definitely, you can just read it, that what it is actually doing. And even after that, what max pool is actually doing. Let's hope this gets trained in time. Yeah. So what we did after that, yeah, once both the convolution layers, we have passed through both the convolution layers, then we can use max pooling. So if you don't know about max pooling, it's very easy. You can just go here and just check max pooling. And it will give you the definition and everything, how to use it. So operator for 2D, okay, that's fine. So first of all, we are using it on the 2D image, that's fine. Yeah, this is the point I wanted to convey. So now what max pooling is doing, you can actually have a pool size, and based on that pool size, if we are passing a matrix, so this is just a matrix representation, what they are saying, showing. So based on this, we can pass it through max pooling layer, and based on this, we can identify that in this part. So if it's 2 by 2, if we just think of this 1, 2, 4, 5, 2 by 2 grid, what if it's max pooling, we will just take out the max portion of it. So in the first grid, what are we doing? It's max pooling. Max pooling as in take out the max number. So we have took out 5. Okay. In the next portion, in next state, which is the max number in 2 by 2 grid, 6. So we have taken out 6. Similarly, if we take it 8 and if we do it here, it's 9. So this is how the output of max pooling is 5, 6, 8, 9. So you will have small examples on different matrices. So just you can see the examples and get to know what max pooling is actually doing. Okay. So this is how. Rest everything we had already discussed some part of it. So that's fine. So just I wanted to convey what max pooling is doing. Yeah, so it's training. That's not an issue. We can actually start the other part of it. Yeah. So let's wait for the training part to complete. I don't think so it should take a lot of time, but just for the interest of time, I will just use the pre-functions that, because I've already explained. So let's use the pre-functions which you have already built in. The functions that we saw here, we can use those directly and print it here. Okay, so once our model training is done, then we can use these. So let's check, and once that is complete, we will have one part of it for evaluation. So what I will do, I will just write the evaluation part here. We won't wait for our training. Training will go on simultaneously, and let's wait here. So 4 epochs are done. So let's see what it's doing. It's actually saying accuracy is pretty low in the first epoch, not an issue. Validation loss is also very high. Okay. Okay. And my validation accuracy is 0.69. Okay. Just a thing. Now, just looking at that, what do you see here? My validation accuracy at the 9th epoch. After model training, the validation accuracy is so low. So even with the test, I'm seeing the validation accuracy is close to 56%. But using CNNs at maybe 3rd epoch itself, I have this much. Let's see with the test data. I'm not concluding anything, but there is a difference, and there is quite a difference from 50. Even if you go to 70, there's a 20% increase, and that 20% increase with less number of parameters do matter. That is the reason why CNNs are so famous for image related tasks, computer vision tasks. Okay. So we will do this and then we will evaluate. Evaluate is nothing but we will just pass out an image to our model and we will just see what the model is predicting. And just for the interest of time, I might use the pre-built code, which I already have for evaluation, because the major chunk of the session was how to create a model that we have already seen and that we completed step by step. But for evaluation part, we can directly see from the pre-built script itself. Let's see how the training goes on. Okay, till now, is there any doubt what we are actually doing? What was the task, from where we started, and what we are trying to achieve? Because if there is a doubt there, then we can talk about it right now. If that is clear, we will just wait for the model to get trained. And by that time, what we can do, this is a very simple script. You don't need to worry about this part because this doesn't come in the model training part. So this is a very simple, it might look what we have typed. So it's just that whatever model that we have already saved, I'm just loading that model. I'm just loading the weights of that model. And what I'm saying, I will just pass in some random test images. Okay. Just passing some random test images. I just want to see the prediction of the model. That's it. So we will do it for MLP as well as let's do it for CNN as well. So what we can do is we can do it for CNN. So I will take it from a pre-built, yeah, CNN itself. So we have not done anything here. It's just the predict function and we are just plotting it. So the output, we can actually visualize the output, nothing else. The major chunk, the most important part was actually completed here, that how we are creating a model and what all layers we have used. And this is a very, very good idea. So if suppose whenever you're creating a model, always print the summary and check what all layers you have used. And just by looking at the layers, you will get to know what all parameters are there, as well as you get to know what are the shapes. And this is very important. In industry, if you're creating a real world application, there can be varied inputs. So to know the shapes of your model properly and at what point it might fail, this portion is very important. Just by looking at this, you might know, okay, in the real world scenario, my output should be this much. That means I should do some pre-processing before it. Otherwise, my model performance won't be that good, or I might see some issues while using it in the production version. Okay. Let's wait. It's 6. Yeah, I know it takes time. It's a good thing that we have used only 10 epochs because training neural networks definitely takes time. We have used the TPU hardware. That's why it's still faster. If we were using only CPU, then it would have been definitely more. So let's hope. I would not extend the session that much. I would need just few more minutes so that it trains. Because the majority of the portion was that should we use CNN? That's already clear that just by looking at this portion, that what is the validation accuracy, and by using the test data, we have seen that what kind of loss we are getting and accuracy we are getting. If we surpass that in CNN using less number of parameters, the session was all about this, and we would know once the model trains that why CNNs are good or why they are used. So let's see, it's 6 epoch. Let's hope it completes quickly and then we can see the result. Usually what happens, we don't usually, for a very small application, we don't use early stopping that much, but I had used it because I was thinking of training it for more epochs. So if suppose we train it for maybe 40 epochs or maybe 30 epochs, it takes a lot of time. And if the model is not improving, then it's better to stop it at that very place. It's not always a good idea to use early stopping. I'm telling you, I'm just using it so that I could have shown it for more epochs, but it's better that we had used only 10 epochs so that our model completes. But just by looking at it, see the loss is quite less because that time validation loss was more, and even the validation accuracy, it's good. So let's hope it works the way we want to. And based on the diagram also, we will come to know. Based on the plot, we will come to know. An evaluation part is nothing. It's just loading the model that we had already created a checkpoint for and just printing the images, nothing else. It's just one line of code. You can just print this and get to know the evaluation just to make it fancy, or maybe just to visualize the things we are using this plotting functionality, nothing else. So this is not important. The important bit is right here. Oh, there's one more thing, right? Yeah, one more thing is that we can actually use the same part what we have used now. Because once the model is trained, we should actually go and evaluate it on the test model that we would be using is same. And yeah, verb was set to 2. It's the 7th. It's okay. It's already 4. I won't extend it way too much. Just few more minutes. Yeah, that is why everybody says that yeah, model training takes a lot of time. This is why. And if you use multiple GPUs, it will definitely be low. But yeah, just by looking at it, it's a very small example with very less number of layers. It's taking this much time. So suppose if you want to continue your training, so if suppose you're creating an application with a, maybe you have epox 200 and you have a very large database. Now training it again and again, it's not feasible. That is why it's advisable to use checkpointing, so that you do the training today. Maybe you're training the model for maybe for 3 hours today, then you checkpoint it. Tomorrow you log back in, train the model for 5 to 10 hours, then checkpoint it, and then just use that checkpoint to train it again, so that all the weights are from the previous checkpoint, so that it doesn't train from scratch. It trains from the last best point of it. Okay. So now we have reached 8 epochs. So let's hope that it should complete quickly. Yeah. And as we see, it also tells us how much time does it take. So it's showing, yeah, 106 seconds. Yeah, it's very less. If you use if you must have used Kaggle or maybe Coursera platforms, they don't use TPUs, I guess. So that's why the time taken there is quite longer than Colab. But if you have access to TPUs on your local machine or maybe university premise, that speeds would be much better. So you can actually train it on your local hardware rather than on cloud. But Colab is a platform that's quite free. So it's much better to train it here because you can just share your work with others and multiple people can just use it at the same time. Okay, we have reached the 9th epoch. Let's hope it completes quickly. Yeah. Seeing the validation accuracy, we would know that it should be around 80%. So it's a drastic improvement compared to the earlier model that we were using. And even the loss is less. So let's just wait for it to finish. And we will just see the graphs as well, that what kind of trajectory our validation loss and validation accuracy is taking. Because training accuracy does matter, but validation is the one that we should be worried about, because that portion of the data that model has not seen, and we are just doing the validation part of it. Yeah, let's hope this completes quickly. ETS 40 seconds. Till then, if anybody has any doubt of what we have done till now, you can ask me, not an issue. Okay, let's wait for it. Yeah, and this is just for identifying how it's done. That's it. I hope I was able to explain what all these different layers are doing, because it's not easy to explain each and individual layer in one session and also do the application hands-on in one session itself. But I wanted to give a slight brief overview. That's why I gave it. If you have any doubts, so then we can actually discuss it. But yeah, you should be aware of these things, and then you should actually go about with the hands-on part, because once you start building a model, that time you would realize, okay, there is one layer but I don't know what the implications of the layers are. And even with the implications, I don't know what parameters I'm passing. And with the change of one parameter, what effect that will put on my model. So it's advised to actually read a certain portion of it first, understand it well, and only then come here and then create your model. Otherwise, once you have to change the model, you won't know that what is actually happening over there. So it's the last epoch. Let's hope it completes. Yeah, it's 86, so it would definitely be better than MLP model. So that is why people generally say for computer vision model, not people. That is why it's generally advised, or maybe if you see in real life situation also, people are using CNNs in computer vision applications because they are giving you better accuracy with less number of trainable parameters. Yeah. Maybe we should have used less number of epochs, but training it for maybe less than 10 epochs would be not justified, because otherwise we won't know if the model is actually running properly or not. Okay, so now we see loss. Loss, the trajectory usually should decrease, so it's decreasing, good. And let's see the accuracy. It trajectory should gradually increase. If we train it more, then it's much better. But yeah, it's increasing. And one more thing that we wanted to check quickly is the evaluation part. So we are just evaluating the CNN model, and based on this, we are just checking this. I know we are just 7 minutes above time. I won't take a lot of time, just a minute. We will just see this and that's it. Yeah. So what we have done, see, the loss is less, the accuracy is more with less number of parameters. That is why CNNs are good for computer vision applications. And this is the last thing, so that you can just visualize it. So if we are using a MLP model, seeing this image, what our model is saying, it is saying 1 with this percentage. So it is saying this number is 1 with certain percentage, 2 with the highest percentage. See, so these all are numbers, what it's actually predicting. And if we see the CNN model, it's actually predicting it like this. So if this digit, it's only recognizing this digit, it's 1, something like this. Yeah. That's all for the session that I wanted to convey. If you have any doubts, you can ask me now. So this was the hands-on session that we wanted to have.
Participants can ask the questions if you've got any. You can either unmute or put it in the chat box. Do we have any questions, participants?
I hope it was clear to everybody. And maybe even the brief introductory session was good for people who are just starting in the deep learning model phase.
Yes. I think Varsha Bhole has got a question, but her
Yeah.
mic is not working. So she said she'll ask tomorrow.
Yeah, no problem. Or maybe she can type the question, or maybe if the question is not directly relevant to the session, so she can just type the question today and we can discuss it tomorrow morning, not an issue.
Yes, ma'am, you can actually type the question and Varsha ma'am. She says she'll ask tomorrow, so that's
Yeah,
okay.
yeah. Okay. Okay, then I'm just stopping the share screen.
Okay. Here, with this, we come to the end of the day 4 session on CNN, the model training. Piyush, it was really nice listening to you. And I've been listening to you even when you were a student, but still this was more better, and I felt really proud of you. And the way you have explained the CNN, the layers, the architecture of CNN, the MLP basics, and the flattened layer, and so on, and the normalization, then the actual training and splitting of the data, and all the minute details and explanation of all the functions and commands used was really nice. And I hope the participants have benefited from it. And tomorrow also you are there, so we'll get the benefits tomorrow also. And tomorrow, I suppose there will be again a big question answer session, as today I've given food for thought for
Yeah.
all of us. So, okay then. With that, we come to the end of this session. I thank all the participants and a special thank you to Piyush. Okay, we will see tomorrow participants at 10 o'clock sharp, and Piyush will see you tomorrow again at 2 o'clock sharp.
Mm.
And
Oh,
then, thank you.
okay.
Goodbye.
Thank you, ma'am.